So, in this question, they've told us a ladder is sliding down the wall. The ladder is 4 meters long. This will be our ladder, which is the hypotenuse. We're going to call the height of the ladder at some point in time coming down the wall will be our A, and how far the ladder has moved from the wall will be calling B. Okay. At this point in time, our equation for the entire ladder for distances of how high up on the wall and how far from the bottom of the wall the ladder is represented by Pythagorean's theorem. A squared plus B squared will equal our C squared in this case. Okay. Now in the question they told us that if the bottom of the ladder, lumber, not ladder, slides away from the wall at a rate of 0.25. So the bottom of the ladder is moving, so our derivative of B over time is actually 0.25 at this given point in time when the bottom of the lumber is 2 meters from the wall. So we're trying to figure out how fast the top of this ladder is coming down the wall. So we're looking for the rate of change of dA over d at t. So we're looking for the rate of change of that when our ladder, our B, is the measurement of 2 meters from the wall. Okay, so we set up our original equation, and I think in your stuff they called it y. We're going to stick with a, b, and c. We're going to call this our c. Okay, our c squared is equal to our a squared plus b squared. Okay, we knew our c squared was the number 4, so we end up at 16 is equal to a squared plus b squared. And then we took the derivative of this. Derivative of 16, any constant number will give us 0. This gives us 2a with the derivative of the change in a over in time. And derivative of b is the change in b over time. Now what they've told us in this question is we have quite a bit of other information. First off, we know that the distance of b at this point in time is going to be 2 meters. So in other words, our B is going to be our 2 meters. Okay, and we also know that the change in rate here is going to be 0.25 meters a second. Yeah, the bottom of the ladder is sliding away at 0.25 meters a second. So our rate of change is 0.25 meters a second. We need to find the rate of change of our other one. Now, what we can do is we can also find out how far away from the top we are at that point. We can use our original Pythagorean theorem to find out the actual height of the ladder at this point in time. So we're going to do that so that we have our variable a, and that we'll only be looking for one thing left over. So first what I'll do is I'll plug everything else in that we just said. So we have our 0 is equal to 2, a, 2 by 2, by our rate of change, which is 0.25. Does this make sense so far? Okay. We're going to plug in our Pythagorean's theorem. We know the distance of the ladder. I'll put the theorem here. Our c squared is equal to a squared plus b squared. We're looking for our a. We know that b is a distance of 2. And c is always the same distance of the lumber, which is 4. That doesn't change. So we have 16 is equal to a squared plus 4. When we bring it to the other side, we get 12 is equal to a squared. We square root both sides. Square root of 12, 3.46. So how high the ladder up is at 3.46 meters above the wall. So we've now solved for our a, and we should use this as a side calculation. This over. This was our side calculation to figure out how high up the wall the lumber was when it reached that rate we were talking about. Okay. So our new equation now reads 0 is equal to the number 2 times 3.46 by the rate of change, which we're trying to solve, plus 2 by 2 by 0.25. Because we only have one equation, we always want to break whatever we're working down into one variable, because with one equation we only have enough information to solve for one variable. So now that we've done that, it's as simple as setting out the rest of the algebra to this. We're going to end up with 2 by 3.46, 6.92. So 0 is equal to 6.92 times our rate of change of A, how fast this ladder is coming down the wall, plus, I think that's going to be 1. 2 by 2 by 0.25 is 1. We bring 1 to the other side of the equation. Does that make sense? Negative 1 is equal to 6.92 by the rate of change. And from there, we end up with the fraction that the rate of change, so how fast it's coming down, which will be a negative because it's in the downward direction. Our rate of change is negative 1 divided by 6.92, or 1 divided by 6. So the ladder is coming down the wall at a rate of 0.14 meters a second. So we're talking about the change of the area in the circle. We know that area of a circle is equal to this equation. At some point, we're going to have the change in the radius of the circle over time will be 3. And we're looking for the change in area over time. Okay? So we've set the equation up. This is our change in area over time. And that will be equal to the change in the area, depending on the change in the radius, because our radius is our major variable which will affect the radius of the circle, times our change in the radius over time, because the more time that's spent pouring, the larger the radius is going to get. So what we're going to do is we're actually going to find something that is equal to the area in this equation. In this equation, we're looking for the change. This is our ultimate answer. Sorry, this is our ultimate question. Change in area over time. So this is what we're going to set up here. Our change in area over time is going to be equal to the change in our area, which is R2 pi, all right, over the change in the radius. All right, does this make sense to you so far? And then we're going to be multiplying by our change in the radius over time. And we have a measurement for that. We'll plug that in after. What we need to do is we need to derive this equation. Okay? So the change in area, depending by the change in the radius, we're going to be left with, this is an actual number. Pi is an actual 3.14. So we actually have to multiply, when we find the radius of this, we'll do it as a side function here. We technically have pi r squared. When I bring that down, or when I derive this function, okay, when I find the derivative of this function, we're going to be looking at 2 pi r. Does that make sense? We're not going to equate into a full decimal just because it's going to be very difficult to work with this very large number. So we're going to be left with 2 pi r times the change in the radius over change in time. Okay. Once we've done that, we actually know what our rate of change is in radius over time. We know it's going to be 3 dr divided by dt. We know that that number will be 3. We just have to piece together one more part because there are still 2 variables. Okay. So we do need to plug in that our change in radius is in 3 meters a second, right? So change in radius over time is 3 meters a second. And we have that here, change in radius over time. So we're left with 2 pi r times 3 meters a second. This will essentially give us 6 pi r is equal to our changing area. Now, let's take a look at this equation. We need to find out what if this is every second, we're going after 4 seconds, and we know the radius change, the rate of in our radius is changing at 3 meters a second, and we've passed 4 seconds, how large is our r going to be? Yeah, that's right. Because it's 3 meters a second, so we know for every second we increase by 3 meters. R is going to be equal to our, this was the small formula I wasn't thinking about. Our radius of our circle will be equal to 3 times s, depending on how much time in seconds has passed. So R equals 3s. Since our s is 4 seconds, we're looking for 4 seconds. Sorry, not 4s, but 4 equals s. We're going to be left with 3 by 4, which is 12. So the radius of our circle at this time will be 12 meters large. So in other words, we'll be plugging in 12 for our radius. So 6 pi by 12. So the rate of change of the area over time at this will be 72 pi, which in this case you get 72 times pi. The area is changing at 226.19 meters a second at this point. It's really meters or millimeters? So that was a bit choppy. Let's go through that again. We have our circle, and we're looking for area of a circle, which we know is r2 pi, or another way you could write it is pi r2. Okay, that's the area of a circle. We're looking for the rate of change of the entire area of the circle. So in other words, we're looking for how fast the area is changing at a certain point in time. Now, in the question, they've told us that the radius of the circle changes at 3 meters a second, and they want us to find the area of the circle after 4 seconds. Right away, that tells us about our major variable, which is the radius of the circle. We know that the radius of the circle is going to be equal to 3 times the amount of seconds that have passed. Okay? So because they want us to find the radius of the circle after 4 seconds, we'll be taking 3 by 4, which equals 12. So at the point in time where we're trying to find what the change in area is, we know the radius of the circle will be 12, and sorry, I've written meters, it should be in centimeters here. 3 centimeters, we know it's going to be 12 centimeters large at that time. Okay, now we're going to relate, because we're looking for, again, our change in area over the change in time. We can split this. Essentially, we can change this into the change in area is related to the change in the radius multiplied by the change in radius over time. The change in radius over time, we have that measurement. We know that it's going to be 3 centimeters a second. And we know that dA divided by dt can be related to this. We know they're equal because if I were to multiply these fractions across, my dr and my dr would cancel out, and I'd be left with the change in area over the change in time. Does that make sense? Okay. So now what we do is we're going to start plugging things in. We're solving for the change in radius over time. Now this part here is essentially this equation, except that I've plugged in the area formula for A. So we know that our area is equal to R2 times pi, or pi R2. So I've replaced the A in that part of the equation with pi R2. Okay. So now that I've done that, I'm going to derive that. And when I derive this, this essentially goes out. We find a derivative of this. We end up with 2 pi r times the rate and change of the radius, because that's this part of the equation, which we haven't solved, a change in radius over time. We do know that the change in radius over time is 3 centimeters a second. So I can replace this part of the equation with the number 3. When I multiply them across, we get 6 pi r. Okay. And the very beginning, we discovered that we knew at this point in time the radius of the circle would be 12 centimeters long. So we're replacing our r, the radius of our circle, with the number 12 at that time. So when we multiply it through, we get 72 pi, and it's not meters, centimeters a second. Or sorry, because it's area, it's actually centimeters squared a second. Okay, so you could relate it as that, or we wrote it down as